In this video lesson, we are going to study alcohols and their reactions. Precisely, we are going to cover the physical properties of alcohol, classification of alcohols into primary, secondary, and tertiary. Tests to distinguish between the different classes of alcohol. We will also be treating dehydration of alcohols using suitable reagents. And finally, halogenation of alcohols to halogenoalkanes. Before continuing with our topic today, please like this video and subscribe to our channel. Do not forget to hit the notification bell. What do you understand by alcohols? As you know, alcohols, they form a homologous series with a general formula CN H2N plus 1 OH. And they have an OH functional group. The hydroxyl group is the functional group for the alcohols. We said they have the general formula CN H2N plus 1 OH. That is their general formula. That is their general formula. And the functional group for alcohol, as I said, the functional group is, they have a functional group of, the hydroxyl group is their functional group. The hydroxyl group, as I said, occurs in many organic compounds, including sugars. They occur in sugars. You can also find the hydroxyl group in phenols. You can also find them in carboxylic acids. This is where you can find the functional group, the hydroxyl functional group. And you should know that this group, the hydroxyl functional group, is polar and forms hydrogen bonds. This group is polar. This group is polar and forms hydrogen bonds. It forms H bonds. You see this, let's say it has, for a group like this one here, check this, you will see that this is a carbon attached to the OH group. You can say this, yeah. You will notice that because of the difference in electronegativity of oxygen and carbon, they one acquire a partial negative charge and they one acquire a partial positive charge. The same thing goes here between the different oxygen and hydrogen is positive. So that's why we say the OH group is polar and it forms hydrogen bond. And hydrogen bond can be formed with, between what? between this the lone pair of electron on this oxygen and another hydrogen atom. So let me just represent this for you to better understand. Okay, let me say I have a group like this one here. I have a CH, let me say, a group like this, which is attached to, we have oxygen, this is an OH, that is an ethanol, this ethanol, this ethanol. Yeah, because of the difference in, or the polarity, as we earlier said, this is as a partial negative, and this is partial positive charge. Then, if there is another hydrogen, if there is, let me say, another water molecule here, it can form hydrogen bonds with. Let me say there is a water molecule here. There is oxygen. There is a water molecule. And this is, yeah. Now, we have a lone pair of electron here on the oxygen, and we also have a lone pair of electron here. What happened is that this is alcohol and this is water molecule. This now can form hydrogen bonds with this. I can donate the lone pair of electron to this hydrogen, and a hydrogen bond is established there. The same way, if there is an oxygen here, let me say there is a and there is another one here. Because of the lone pair of electron here, a hydrogen bond can be established between this one here and the oxygen here. Then again, another hydrogen bond can be established here too. That is how the thing continues, and that is how it is. So you see the polarity as it is: partial positive, partial negative, partial positive, partial positive, partial negative, and partial positive. Indirectly, I'm saying that this is what I said: hydrogen bonds. Hydrogen bonding. Now, what am I saying? I am indirectly saying that alcohols, lower alcohols having between 1 to 4 carbon atoms, let me say methanol, ethanol, propanol, butanol, all of them are lower alcohols. They are miscible with water. They can dissolve in water because they can form hydrogen bonds with water molecules. This is a water molecule here. These alcohols are miscible in water because they can form hydrogen bond with water molecules. So I said lower alcohols lower alcohols are miscible in water. They are miscible in water. They are miscible with water. They are miscible with water because they can form H bonds with water molecule. They are miscible with water because they can form H bonds with water molecule. Remember that as the carbon chain, as the number of carbon are increasing, what happens? As the number of carbon atoms are increasing, or as the alcohol become larger and larger, van der Waals forces will now predominate. As the molecules are becoming larger and larger, maybe from hexanol, heptanol, to higher alcohols, what happens is that the van der Waals forces will now predominate. The forces there will no longer be hydrogen bonds, but there will be van der Waals forces between the molecules of the alcohol. So as the number of the carbon chain is increasing, van der Waals forces predominate. So I can say higher alcohols have strong van der Waals forces. They have strong van der Waals. Van der Waals they have strong van der Waals forces. So for that reason, because of the strong van der Waals forces in higher alcohols, what happens? The miscibility with water decreases. In other words, I am saying that as the alcohols increase, or as the carbon chain in alcohol is increasing, what happens? The van der Waals forces are increasing. And when the van der Waals forces are increasing, miscibility with water decreases. Implying that higher alcohols can no longer be miscible in water because of what? Because of the strong van der Waals forces present in them. So that is the thing. And this now drives us to classification of alcohols. Classification of alcohols. It now drives us to classification of alcohols. You know that alcohols can be classified into primary, secondary, or tertiary alcohols, depending on the number of the alkyl groups that are attached to the carbon atom that is bonded to the hydroxyl group. The number of alkyl groups attached to the carbon atom bonded to the hydroxyl group will determine the class of alcohol. In this case, where the carbon atom bonded to the alcohol group is attached to only one alkyl group, we call it a primary alcohol. Where the carbon atom bonded to the hydroxyl group is attached to two alkyl groups, we call it the secondary alcohol. And where the carbon atom bonded to the hydroxyl group is attached to three alkyl groups, we call that one a tertiary alcohol. You will not understand this unless it is demonstrated. And let me use this example for you. Let's start with there is methanol. I start this one as there is carbon. I want to give the display structure of it. Hydrogen. Let me write this so that you will better understand what I'm saying about the different classes of alcohol. R1 stands for the alkyl group. Okay, I have said where I have said that when the carbon atom linked to the OH group, this is the carbon atom. This is the carbon atom that is linked to the OH group, to the hydroxyl group, is bonded or is attached to one alkyl group. For example, here, this is a carbon atom that is bonded to the hydroxyl group, which is the functional group. When it is attached to one alkyl group, here, the alkyl group R1 is arrow. Let me represent it to be arrow. R1, R2, R3, these are all alkyl groups. The alkyl groups could be a methyl group, it could be a ethyl group, it could be a propyl group, it could be a butyl group, and so forth. So now, if one of the hydrogen is replaced or is substituted by an alkyl group R1, we will call this one a primary alcohol. If two hydrogens are replaced by two alkyl groups, R1 and R2, here, like this one here, we will call that a secondary alcohol. If there are three hydrogens, 1, 2, 3, are replaced by three alkyl groups, R1, R2, R3, we call that a tertiary alcohol. Once more, I said the alkyl group could be a methyl group, it could be an ethyl group, it could be a propyl group, or it could be a butyl group, and the number increases as you want to do. Okay, for better understanding, let me substitute this into real alkyl groups that you can see. You can see. Okay, let me take the first one. As we said, this is methanol. I want to substitute them with real alkyl groups so that you can better understand what I am saying. Let me represent this first one as substituted by an ethyl group, which is yes. Let me put this one here. Then with the hydrogens. Let me still use this. Yes. This other one here. Let me use a methyl group. Let me use a methyl group here again. You will see here that the naming will have here, this is methanol. This is methanol. This is primary alcohol. And the name here would be what? The name here would be propan 1, 2, 3. Propan 1-ol. Propan 1-ol. The name here will be, this is, okay, the carbon atom, where the carbon atom is carbon atom bonding to the hydroxyl group is attached to what? To alkyl group. We call this a secondary alcohol. Secondary alcohol. And in that case, we will call this, the alcohol is located, there is carbon 1, carbon 2, and carbon 3. The alcohol is located on the second carbon atom. So we say it is propan 2-ol. Now, we now go to the last one. The last one, which is, we have 1, 2, 3, where the carbon atom holding the hydroxyl group or the functional group is attached to 1, 2, 3 alkyl groups. We call that a tertiary alcohol. And that name precisely, in naming them, since it is carbon 1, carbon 2, and carbon 3. On carbon 2, there is an OH group there, and there is a methyl group there. We now say it is 2-methyl propan 2-ol. 2-methyl propan 2-ol. 2-methyl propan 2-ol. This is how you can name them. So now, this is how you can name the alcohols. By doing this, you know the different classes of alcohol, and you can now name them based on the number of alkyl groups, or classify them based on the number of alkyl groups that are attached to the carbon that is bonding to the OH group. Now it leads us now to some practical distinguishing tests for alcohols. Some practical distinguishing tests for alcohols. For instance, if you are given, there are two types of tests we can use to distinguish the different classes of alcohol that we have just mentioned above. We have the first test is oxidation. We can use oxidation reaction test to distinguish between the different classes of alcohol using what? Suitable oxidizing agent, such as acidified manganate 7 solution, or acidified potassium manganate 7 solution, or acidified potassium dichromate 6 solution. So these are potential oxidizing agents that we can use for to distinguish between the different classes of alcohol. For instance, let me say you are given three different alcohols. We have primary alcohol, test tube, secondary alcohol, test tube, and the tertiary alcohol, test tube. These are three different test tubes containing the different classes of alcohol. And you are asked to identify the tertiary alcohol using a suitable oxidizing agent like potassium, acidified potassium dichromate 6. I want to use acidified potassium dichromate 6 for this. You could equally use acidified potassium manganate 7. So now, if I'm using acidified potassium dichromate 6, here I will have, let me say, a CRO. Solution. I am using acidified potassium dichromate 7 solution as a suitable oxidizing agent. Or you could use this. Or you could use acidified potassium manganate solution. You could use acidified potassium manganate, acidified potassium manganate 7 solution. If I use acidified potassium manganate 7 solution, or acidified potassium dichromate 6, acidified potassium dichromate 6, and I am asked to differentiate between the different alcohols. The different alcohols have been placed into three different test tubes. How am I going to differentiate them using this suitable oxidizing agent? The first thing I will do is I will warm each class of alcohol. The primary alcohol, I am going to warm the primary alcohol test tube. I'm going to warm it with this solution of acidified potassium dichromate 6. I will also warm the secondary alcohol test tube with the solution of acidified potassium dichromate 6, as well as the tertiary alcohol. When I warm all these alcohols, my observation will be this. My observation will be there will be an orange precipitate in primary and secondary. There will be an orange precipitate that is formed. An orange precipitate that is formed in the test tube containing primary and secondary alcohol. An orange precipitate there will turn what? An orange precipitate in test tube in primary and secondary alcohol, the orange precipitate will turn green. The orange precipitate of the primary, and the secondary alcohol will turn to a green color. It will turn to a green color. Orange precipitate of primary and secondary alcohols. Orange precipitate of primary and secondary alcohol will turn green. Will turn green. It will turn green. Why will it turn green? The reason is that the orange dichromate ion, is what? Is reduced to green. Is reduced to green because it is reduced from +6. It reduced from +6 to what? To +3. There's a reduction that is taking place as a result of the oxidation of it. So once more, I am saying that the orange precipitate of the primary and secondary alcohols will turn green as a result of their oxidation. So the dichromate will reduce from +6 to +3. Meanwhile, in the tertiary alcohol test tube, no oxidation will take place. There will be no oxidation taking place there because there's no hydrogen on the carbon atom. For instance, here, look at the primary alcohol here. As you see the primary alcohol here, the primary alcohol here will be oxidized. The secondary alcohol here will be oxidized because they all have hydrogen attached to them. But the tertiary alcohol will not be oxidized because there's no hydrogen on the tertiary alcohol. So no oxidation will take place. And the color will only remain. The orange precipitate will remain there. So that's why we are saying that the test tubes for primary alcohol and secondary alcohol, the orange precipitate of the test tube of the primary and secondary alcohol will do what? Will turn to green as a result of their oxidation. The dichromate will be reduced from +6 to +3. And this can be observed in these test tubes here. The test tube is propan 1-ol, which we just discussed. The other one is propan 2-ol, and there is 2-methyl propan 2-ol. You will see that this is the propan 1-ol is the primary alcohol. This is the primary alcohol. This propan 2-ol, this is a secondary alcohol. And this 2-methyl propan 2-ol, this is a tertiary alcohol. We said all of them, that all the test tubes will be what? Will be orange precipitate. All the test tubes initially are orange precipitate. They have orange color. But on reacting them or warming them with acidified potassium dichromate, what happens? All of them, primary and secondary, will turn what? Will turn to green. Primary and secondary alcohol will turn to green. Meanwhile, the tertiary alcohol the orange precipitate in the tertiary alcohol will remain because there's no reaction that has taken place. The turning, the change in color, or the change in the color of the precipitate of the primary and secondary alcohol from orange to green indicates that oxidation has taken place here in the primary and secondary alcohol. And as a result of it, we can now conclude that this is due to what? The reduction of the dichromate, from the orange dichromate to what? To 3 plus. The orange dichromate have been reduced to what? To plus 3, which is the green color of it. Meanwhile, the tertiary alcohol remains. So these are the different alcohol: propan 1 all, propan 2 all, propan 3 all. Now the test tube, we are treating them with orange. We are treating them with acidified potassium dichromate. The first two, the color will change from orange precipitate to green, but tertiary alcohol will remain orange because there's no oxidation taking place there. Now, that drives us to another test for distinguishing alcohols. The third test is the Triadomethane Test. Triadomethane Test, or what we can call the Iodoform Test. The Iodoform Test, this is a test to identify the presence of the CHO group in alcohol, to indicate what? To identify the presence of the secondary alcohol in alcohols. This is to what? To identify the presence of CH3 CHOH group in alcohols. In an alcohol. This test is to identify the presence of this group in an alcohol. Now, alcohol that contain this group, you should remember that alcohols that contain this group, that is the CH3, CH, alcohols that contain this CH3CHOH group, that is, I am saying that alcohols that contain a methyl group, and a hydrogen, a methyl group, and a hydrogen atom attached to the carbon atom that bears the hydroxyl group, can can be oxidized using alkaline aqueous iodine. Once more, alcohols that bears the methyl group and a hydrogen attached to the carbon atom bearing the OH group can be oxidized. They can be oxidized using alkaline. This can be oxidized using alkaline aqueous iodine. Alkaline aqueous iodine. Alkaline aqueous iodine. They can be oxidized using alkaline aqueous iodine to what? To their corresponding carbonyl compounds. This can be oxidized using alkaline aqueous iodine to their corresponding carbonyl compounds. And if we oxidize this, we will have this. What will the corresponding carbonyl compound? The corresponding carbonyl compound will be what? Will be a methyl ketone. Will be this. So alcohols containing this group can be oxidized using alkaline aqueous iodine to their corresponding what? To their corresponding carbonyl compound, this one, the methyl ketone, which will not undergo, it will not undergo triiodomethane reaction, which will undergo triiodomethane. The triiodomethane. We will undergo the triiodomethane reaction. It will not undergo the triiodomethane reaction. Now, it should be remembered that all secondary alcohols, the secondary alcohol will do that. The only primary alcohol that can undergo this is ethanol. This is only done by secondary alcohol. But there is one exception, which is the primary alcohol that can undergo this test. And that primary alcohol is ethanol. Ethanol will give a pale yellow precipitate of triiodomethane. Exception, primary alcohol the only primary alcohol of exception is this one. Only ethanol can do that. Only ethanol, which is a primary alcohol, can undergo this. So the only primary alcohol that can undergo this reaction is ethanol. That's why I said ethanol will give a pale yellow precipitate of triiodomethane or iodoform reaction. Okay, in this case, for you to better understand this, I would like us to do some reactions here. There are some stages we will undergo for this reaction. I said once more, the triiodomethane or the iodoform test is a test that is used to identify the presence of the CH3CH OH group in an alcohol. And this group can be oxidized using can be oxidized using alkaline aqueous iodine. You will oxidize this group using alkaline aqueous iodine to their corresponding carbonyl compound. This carbonyl compound will now undergo what we call the triiodomethane reaction. So we want to use an example of ethanol. We want to use an example. Beside ethanol, we want to use it. So the alcohol, the first step in this is that the alcohol is oxidized by alkaline aqueous iodine to what? To methyl ketone. Let me use this. This one is oxidized. The alcohol is oxidized by alkaline aqueous iodine solution to form what? Methyl ketone. I want to use this example above, and we do it. Here we have CH3, step 1. Step number 1, we will have CH3, CH, CH, it will undergo oxidation to form what? We will have, we will have here alkaline aqueous iodine. Okay. Alkaline aqueous iodine. Now, it will undergo a to form what we call this a methyl ketone. This is a methyl ketone. This is a methyl ketone. Now, step number two will be what? Step two. In step number two, I said the methyl ketone is halogenated. The methyl ketone is halogenated. What do I mean by that? The three hydrogen atoms, are replaced by iodine atoms. The methyl ketone is halogenated. The methyl ketone is halogenated. This is how the equation is going to be. We will have this is the methyl ketone. This is the methyl ketone will undergo halogenation. It will undergo halogenation to produce an intermediate. You now see where the oxidation has taken place. I mean the halogenation has taken place. This is an intermediate. This is an intermediate. It's an intermediate. Here, there's halogenation. There's iodine. Yeah, alkaline aqueous iodine is still there. So now that the methyl ketone is halogenated by doing what? The hydrogen atoms will replace this. The iodine atom will replace the hydrogen atoms here, and you find it in this intermediate. The step number three in this iodoform reaction. Step three. Step number three. The intermediate is now hydrolyzed to form the yellow triiodomethane precipitate and a salt of carboxylic acid. Hydrolysis of the intermediate. I said in this step, the intermediate is hydrolyzed to form the yellow triiodomethane precipitate and a salt of carboxylic acid. This is the reaction. That's alkaline hydrolysis. And when there's hydrolysis, what happens? This structure is formed here. And we can now call this one here triiodomethane yellow precipitate. Triiodomethane yellow precipitate. This is the triiodomethane yellow precipitate that is being formed here. This is the triiodomethane yellow precipitate that is being formed here. So once more, let me explain to you again. I said step number 1. This test can be used to identify the presence of the CH3CHOH group in an alcohol. And this is usually a secondary alcohol. The secondary alcohol, I gave this example here, can be oxidized using alkaline aqueous iodine. When it is oxidized using alkaline aqueous iodine, it is oxidized to its corresponding carbonyl carbonyl compound. In that case, it will be what? It will be a methyl ketone. Now, that carbonyl compound will now undergo triiodomethane reaction. But I told you that there is only one secondary and there is only one primary alcohol that can undergo this. The only primary alcohol that can undergo this type of reaction is ethanol. Ethanol is a primary alcohol and it can undergo this type of reaction. Using our example above, I want to show how this reaction takes place. The first step in this reaction is the alcohol does what? The alcohol is oxidized by an alkaline aqueous iodine solution to form what? To form a methyl ketone. This is the alcohol, which is here. It is oxidized using an alkaline aqueous iodine to form what? A methyl ketone. Iodine plus the alkaline. Okay, a methyl ketone. Step number 2, the methyl ketone is halogenated to form what? The methyl ketone is now halogenated. Okay, now for it to be halogenated, what happens? It is halogenated under the same condition, alkaline aqueous iodine. Now under the same condition, what happens? The hydrogen atom here are replaced by the iodine, as you see it. An intermediate is formed. Step number 3. You know that an intermediate is unstable. So step number 3 to finalize it. The intermediate is now hydrolyzed to form what to form the yellow triiodomethane to form the yellow triiodomethane precipitate, and the salt of what? And the salt of a corresponding carboxylic acid. In that case, this is it. It is now hydrolyzed. During the hydrolysis, what happens? There is a breakage here. During the hydrolysis, there is a breakage there. Now, what happens? The oxygen here attaches itself here to form the two oxygen you are seeing here. And the hydrogen in this alkaline does what? Is added to this triiodomethane. It is added here to form what? To form the CHI3. And that CHI3 is now what we call the triiodomethane yellow precipitate. It appears, the yellow precipitate will appear in the test tube. And that's why you find it. Another second example of this, I said a primary alcohol that can undergo this is ethanol. Which is the only exception. This is ethanol. I want to use ethanol here as an exception. This is ethanol. Now, what happened with ethanol? It will undergo oxidation. It will undergo oxidation. What? Alkaline aqueous iodine. So have iodine there. Plus now what now happens? This is the product that is formed from there. We will have CH3. Remember, primary alcohols are oxidized to what? They are oxidized to aldehydes. So it is now oxidized to what? Ethanol. It is oxidized to a corresponding carbonyl compound. This is the carbonyl compound. So now the carbonyl compound now will undergo what? It will undergo halogenation. After the oxidation, there will be halogenation. Halogenation with halogenation with iodine atoms. Okay, halogenation with iodine. Now, still under what? Alkaline. Yeah. So now, during this period, as it is undergoing halogenation, what is happening? There is a breakage here. There is a breakage here. A breakage is taking place there. And the result of our product will be what? We will have a C, H, I3, which is solid, that is the precipitate. The precipitate, and what? That will be formed. So you can now see that iodine, ethanol is a good example that we can use, and this will be the formation. This is a yellow precipitate. This is a yellow precipitate. This is a pale yellow. pale yellow precipitate. Now, it drives us, and that is, and you can find it here even with another example is butan 2-ol. Butan 2-ol will undergo the oxidation to what? To butan. This is butanone, or what we call butan 2-one. Butan 2-one. Then it will undergo what? It will undergo halogenation to form this. And now after that, hydrolysis to form the triiodomethane precipitate. These are the precipitates that are formed here. It takes us now to dehydration of alcohols. Alcohols can be dehydrated under some conditions. The condition of dehydration of alcohol, we have excess concentrated sulfuric acid that we can do it. Other excess concentrated sulfuric acid, phosphoric acid, or catalyst, which is the hot aluminum oxide. You can heat it to about 170 degrees Celsius under reflux. When you dehydrate alcohol, you will get your corresponding ethane. So an example of this is, I'm talking of ethanol, which is this. Ethanol, CH2OH. We can do this to have ethane, which is this, plus water. You do that, you can get ethane. And the condition for this, as I said, will be excess concentrated sulfuric acid. Excess concentrated sulfuric acid, heating it at about 170 degrees Celsius or above. You have the thing. Examples, these are good examples of it. You can see butan 2-ol was dehydrated using this condition, and there are two isomers that we got there. We had but1-ene and but2-ene. These are two isomers produced by dehydrating butan 2-ol. Another example of this dehydration is propan-1-ol. Propan-1-ol, if heating it with concentrated sulfuric acid at the temperature of 170 degrees Celsius, will give rise to what? Propene. A molecule of water is removed. So these are examples of dehydration of alcohol. It now takes us to halogenation. It takes us to halogenation of alcohols. Alcohols can be halogenated to form what we call halogenoalkanes. This is what we call nucleophilic substitution to give what? To give nucleophilic substitution to give what? To give halogenoalkane. The nucleophile is the halogen that now substitute the OH group to give a halogenoalkane. There are three sources of the halogen. It could be from the halogen. There are three sources of halogen. It could be from a hydrogen halide. If we are using hydrogen halide, for example, let me say the source of halogen, let me say CH3, CH, OH plus 2 hydrogen bromide. The hydrogen halide, for example, hydrogen bromide, we will have the halogenoalkane that we will have will be bromoethane, plus water plus HBr that we have. Now, if we were to use, if another source is phosphorus halide, if we were to use phosphorus halide like phosphorus pentachloride, PCl5, or phosphorus trichloride, yeah, OPBr3, OP. If we were to use this will be our equation. Let me use ethanol again. We have CH3, CH2, OH, plus, let me use phosphorus pentachloride. To have our halogenal alkane, we will have CH3, CH2, Cl, plus and this compound, these are what we call white fumes of hydrogen chloride. White fumes of hydrogen chloride. Another source is thionyl chloride. Another source is thionyl chloride, which is thionyl chloride. Another source is thionyl chloride, which is SOCl2. I use this to be the same CH3, CH2, plus that's thionyl chloride. Our halogenal alkane will be CH3, CH2, Cl, Cl plus sulfur dioxide gas plus HCl plus HCl gas plus HCl. So halogenal alkanes take place. The sources of halogenal alkanes are from hydrogen halide, from phosphorus halide, or from thionyl chloride. If I were using ethanol plus hydrogen halide, for example, hydrogen bromide will give us this. Another one, if I was to use phosphorus halide, and I'm using ethanol, this is our halogenal alkane will be chloroethane, and the white fumes of hydrogen chloride. If I was to use this last one, we call it the thionyl chloride. We will still have chloroethane, sulfur dioxide, and hydrogen chloride. So we have three sources: hydrogen halide, phosphorus halide, and phosphorus halide, and what? And thionyl chloride. These are the sources of our halogen. So this is how you can halogenate alcohols to halogenoalkanes. Learners, if you haven't subscribed to our channel, please subscribe and hit the notification bell. Thank you for watching.